Hi all, this is Mr. Yeager for AP Physics. Today we're looking at the topic of what we call gravitation. Gravitation. And this is obviously mainly covering the idea of gravity and gravitational force, which you might be sitting there saying, well, I already know about that. We've already talked about gravity. The acceleration due to gravity is 9.8 meters per second squared, which we round to 10. And gravitational force is also known as the weight, which would just be m times g. Why do we have to cover this in a little bit more detail? Well, that's because we don't only want to figure out obviously the idea of gravity and gravitational force on Earth, but we want to look at it from a universal standpoint, from an astronomical standpoint with all the planets and how they move around their particular stars or suns, and or how about the moons orbiting around each other, around the planets. Okay, so we want to know a little bit more where these things are coming from. And so if we jump straight into it, we already know this first definition. Gravitational force is the attraction between two masses. Okay? There's gravitational force between all of us. All right? There is this gravitational force attraction between every object. It turns out it is very, very small between smaller objects. Okay? It has to obviously be felt. The only way for it to be felt is for it to be a larger, more massive object like a planetary-sized object. There have been experiments to prove it on Earth with smaller objects, but those are things you can find elsewhere on YouTube and go, show me gravity experiments, and you can see those. So it does exist between everything. It is considered one of the four fundamental forces in physics. All right, fundamental forces. All right, it is actually the weakest of all the fundamental forces. The other fundamental forces out there are the strong and weak forces that basically are your nuclear forces between molecules and atoms, atomic bonds basically, and even smaller than that. And then you have electromagnetic forces, which is your obviously electrical and magnetic force. Then you have this gravitational force is the fourth of these fundamental forces. You only need to learn about this one and a little bit about electric force in AP Physics 1. All right. So getting back to this, sorry. It is again attraction between two objects. We basically know it's going to be related to their masses, proportional to their masses, and it's going to be inversely proportional to the square of the distance between the two objects. All right. And so that leads us to our formula, which is right down here. Gravitational force equals G m1 m2 over r squared. Over r squared. All right. The main types of questions you see in AP Physics with these is ones where we'll do one or two, where what happens if you double the mass? What will happen to force? It should double. What happens if I double the distance between the two objects? Well, that's a square relationship. It's going to be a quarter because it's an inverse square relationship. So those are really the bigger questions you're going to be asked about with gravitation is relationships within the formula itself. So be prepared for those. The universal gravitational constant, that's what big G is. It is 6.67 times 10 to the negative 11th, and with a lot of those units, Newton meters squared over kilogram squared. That is again given on your formula sheet. You do not need to memorize that, but obviously if you use it enough, you should probably get a handle on it. The other ones I have here, not worth memorizing. They're actually on your formula sheet as well. The first one is the mass of the Earth, the radius of the Earth, and the second one is the mass of the Sun. I give those often because obviously a lot of problems involve what's the gravitational force between the Sun and the Earth, or Earth and an object, and so forth all over the place. So again, what we're looking at now is what if you are farther beyond Earth, okay? How can you use these formulas? And we would use this gravitational force formula down here, G m1 m2 over r squared. The second part of this is really just what is G? What is little g? Okay, which we always have said 9.8 or 10. Again, in AP Physics, you can use 10. The gravitational field is, again, that invisible, I don't want to call it a force. I mean, as it says, it's an invisible field, like an electric fence for dogs. All right, this invisible field that surrounds a mass. All right, every mass creates its own gravitational field. The one that I always like to joke about is the one from Family Guy where they show the one episode where Peter has his own gravitational field. All right, we all actually have our own gravitational field. It's just not going to be very strong because of the size of our mass. What the field is, we've talked about field forces before. Okay, the field is what will help create the force on another object, not on itself, on another object. And obviously, that is what's going to eventually create your force. Okay? So that's why we have, this is the other formula for gravitational force, m times g. This is the gravitational field acting on a mass outside of it. Okay? Not its own, on a mass outside of it. And that leads us to our second formula. Okay? Lowercase g is equal to big G, the universal gravitational constant, times m of the object we're finding the field for, divided by r squared. So once again, we get the same sort of relationship where mass is directly related, all right, to g, while its r squared is inversely related to g. So again, what we're going to be interested in is, if I double the mass, if I half the radius, what happens to g? And you can see what we're talking about. Obviously, you're going to have a very small mass. We already said g is 6.67 times 10 to the negative 11th, so that's very, very small. Okay? And then the radius, again, coming from what we basically say is the center of your mass outwards, is not going to be very large either. Okay? Which might increase it, but not that much. Okay? So that's what we're looking for, okay? We're going to be using both of these formulas in these problems, mainly with relationships. All right? So one of the first problems we always like to do is, let's go ahead and prove that the gravitational field of Earth is 9.8 meters per second squared. Well, how do I do that? I use the formula. I go lowercase g is equal to 6.67 times 10 to the negative 11th times mass of Earth, 5.97 times 10 to the 24th over r squared, 6.38 times 10 to the 6th. Now, I've seen students generally 90% of the time do these very, very well because it's a pretty straightforward formula. The biggest mistake is people forget about the square. Please make sure you follow the formula. All right. Obviously, be prepared to calculate with scientific notation well. That's usually the other mistake. So it's silly mistakes for people that get these wrong. But I'm confirming for you. And I get G equals 9.78. All right, 9.78. Now, if I leave this with the units, I already know it should be meters per second squared. If I want to actually put all the units into this, let me see if I can figure that out. It would be Newton meters squared over kilogram squared. So this would be times kilograms divided by meters squared. So meters would cancel out. So the gravitational field, and this is something else to notice, does equal newtons over kilograms, which makes sense because it's when we do this formula, force, it's m times g. If I do kilograms times newtons over kilograms, I get newtons for force. All right. Again, sorry, a little bit of sidetracking there. But don't be surprised if you see this as the units in your answer. Okay, the units for multiple choice questions, which actually, it turns out, equals meters per second squared. So newtons over kilograms is actually the same thing as acceleration, meters per second squared. Okay? So I think we just have a couple other problems we're going to look at here. Let's go. Okay? So what is the gravitational force between two packages? 15 kilogram packages that are 35 centimeters apart. All right? Let's go ahead and solve this. So this is Fg equals G m1 times m2 over r squared. Really nothing much to this. I use these just to make sure my students know how to use the formula. Okay? I'm going to do 15 squared because the mass is the same, 15 times 15. I have to have centimeters and meters, 0.35. Also square that because that should be squared. I'm not multiplying 2, but that should be squared. And this will kind of show you how small gravitational force is between two more normal objects. Okay, so this 15 kilogram package is pretty big. All right, 1.23 times 10 to the negative 7th newtons. All right, that is more like how the gravitational force between two people. 15 kilograms is only about 30 some pounds, so it'd be between two little, like basically toddlers. But again, even though they're very close, very little force between them. Frictional force will be able to stop those two objects from moving toward each other. Okay, but just showing how to use the formula. Okay. If Earth should shrink but its mass remain the same, what would happen to the value of g on Earth's surface? So this is one of those relationship questions. We're looking at g is equal to gm over r squared. Okay? So if Earth should shrink, that means I am decreasing r. I'm decreasing r before I even square it. That's the other thing to notice. What would happen to the value of g on Earth? Mass is staying the same, so my relationship is again relating this. Whenever I do relationship questions, I tell my kids, get rid of everything that stays constant and only leave what's changing on either side. Okay? And so I can tell, since it's in the denominator, if I decrease r, I'm actually going to increase my gravitational field. Okay? It turns out, basically, it's somewhat related to density. The denser the object, the greater the gravitational field is really going to be. Okay? Good. Number 3. Neptune orbits the Sun with an orbital radius of 4.495 times 10 to the 12th meters. If Neptune has a mass of that, and the Sun has a mass of 1.99 times 10 to the 30th kilograms, what is the gravitational force? Again, this just again shows me that you know how to put the formula together, that you don't make silly mistakes with the numbers. And it takes up a lot of space. Oh, look at that. Not even listening to my own advice. Let's put in the right numbers here. Squared. Okay. All right. You should really be doing this as well. Gravitational force between the Sun and the farthest planet outside. We ignore Pluto, which technically is no longer a planet. Hasn't been for quite some time now. 6.7 times 10 to the 19th newtons. Obviously a very large amount of force, but you're talking about two large planetary objects, a star and a planet. Okay, so that's basically what you are playing with. I will tell you on these as well. On the AP test, sometimes they don't worry about the actual coefficient numbers. The questions will say approximately what would be the exponent? What would be the exponent for your answer? And so obviously the faster way to do this is if you know how to add exponents when you multiply scientific notation and subtract exponents when you divide. So I mean, if you look at that, we got 55 minus 11 is 44. All right, minus 24 is, we know it's around 10 to the 20th power. What you need to do is understand, obviously, it's going to be plus or minus 1 because of the coefficients, possibly increasing or decreasing the coefficients. So that's another method just to pay attention to. The problem might not say calculate everything, just what's the approximate amount for the exponents. That's another thing I've seen on AP tests. All right. So here's one more, obviously, where you just have to rearrange and make sure they know how to rearrange the formula and solve for something else. So we're looking for what's the mass of Mercury. So we know the force between them, 8.99 times 10 to the 27th. Okay, a little bit larger, obviously larger because it's so much closer. Okay, equals, let's see here, we're going to use 6.67 times 10 to the negative 11 g times mass of the sun times unknown mass of Mercury divided by 6.98 times 10 to the 7th, which again, I need to square. Please square it. That's the most common mistake I see people do on these problems, is they forget to square. All right. Possibly the question might go, what's the mass based on the exponent? We could obviously do that as well, but I'm going to get an official answer. And the mass of Mercury is around 3.3 times 10 to the 23rd kilograms. 3.3 times 10 to the 23 kilograms. All right, so that's the last problem I have listed for basically being able to use the formulas from a very, very basic standpoint. All right, what we're interested in now is one of the major ways we like to use the formula, and that's through what we call satellite motion or orbiting motion. Okay, and so what we need to go, this is where we connected back to circular motion. All right. In circular motion, when a satellite's going around and around, if we especially follows uniform circular motion, if it follows uniform circular motion, all right, the only force pointing towards the center would be gravity. All right, it'll feel the net force towards the center of the circle, and that net force will equal force of gravity. Okay, force is gravitational force. All right. Now this is where it's a little unique. Obviously you've always learned gravitational force always points straight down. That's when you are on Earth. When you are obviously orbiting around Earth, it's going to be pointing in any direction of where the object is at that particular time, pointing towards the center of the circle, the center of the orbit. And again, even though we might say some of these orbits are ellipses and so forth, we're going to say they're all following uniform circular motion. Now, you can see I have mg crossed out down here. We are not going to use m times g, okay? Because g, if I use g as 10 meters per second squared, I am saying the satellite is on the Earth. The thing is, I'm getting it farther from the Earth. I'm increasing that radius. So what's going to happen to g? Well, the g is going to decrease. And so therefore, I don't want to sit there and be like, well, how much is it decreasing? I want to use the actual gravitational force formula that we've been using in the last few problems, Gmm over r squared. So the most common question that you're going to get is going to be like, if you want to keep this at a constant, if this object is staying in uniform circular motion, the most common question will be, what's the velocity of the satellite? So that's what I'm going to show you here. Obviously, there's some variations to it, but this is the primary formula. So what we're doing is, if I'm trying to find velocity, this is the formula I start off with. Net force equals F of g. Now, the thing is, a couple things we have to realize. What is net force when I move in a circular motion? That is mv squared over r. What is this mass? This mass is the satellite. This is the satellite mass. The satellite is what's in circular motion. It's feeling the net force, not the Earth. Technically, you could say the Earth is through third law pulling back, but we're not going to get into that at all. All right. But this is the mass of the satellite times its velocity squared times the radius, the distance from the center of the Earth. How far away is it going from? How far away is it rotating around? On the other side, I'm going to use my larger gravitational force formula. So G times mass of the satellite. What is it interacting with? The mass of the Earth. So those are my two masses over r squared. Well, this leads us to something very interesting. Okay? We have similar variables on both sides of the equation. So what can we do? We can cancel out what is on both sides. So guess what? I don't care about the mass of the satellite. All right? The mass of the satellite is actually not going to affect the velocity, which is weird, but it's based on the formula. That's what's going to work out. We don't care about what the mass is going around and around and around. It could be anything at this particular radius. I have one r on the left side. I have r squared on the other. So I can cross out r, and I can then cross out the square. I still have r on the right-hand side. So that leads me to the formula. The velocity of the satellite will equal v squared will equal universal gravitational constant times the mass of the Earth over r. Which then if I simplify that more and take the square root of both sides, I get v equals the square root of g mass of the Earth over r. And there you go. Okay? That is a formula that actually will work every single time to figure out the velocity of an object at any particular radius around a planet. So it doesn't have to be Earth. Obviously, this one is Earth. A lot of times this is written as MP, any planet. Okay, MP. So it looks like a C. Okay, MP. All right. So that is the velocity of any satellite, any moon. It doesn't have to be a satellite. I mean, satellites are obviously moons and Earths, planets, and other things like that. It could be anything involved here. This would be your formula. All right. And so again, be prepared for those relationship questions. What happens if I increase r? If I increase r, velocity should actually decrease. Okay, it should have to actually, it won't go as far. What happens if I decrease the mass of the planet? Obviously, the velocity will decrease. All right, you're going to have to be able to do relationship questions with those. All right, and so this is kind of wrapping up what we've talked about. To find the velocity, we need only the mass of the planet or star and the distance between the two objects. We actually don't need the mass of the satellite. Okay, and I go over this because this was a question. They might say, which of the following do you need to figure out the velocity of the satellite? And they'll give you the whole list. You need to recognize what you don't need. Okay, so we don't need the mass of the orbiting object, and it leads us to this formula here: square root of g times mass of planet. This is mass of planet over r. One last thing to point out with this. Okay, and this is just where sometimes people just get confused with it. I've seen problems where you have your satellite, okay, orbiting around the Earth or some planet, okay, orbiting around and around and around. All right. They will say the satellite is a height above the planet's surface. Okay. What they're referring to is from the surface up. They will give you that height. Okay. The thing is, the gravitational force comes from the center of the planet. And so, you need to make sure you add in the radius of the planet as well. So the total distance, r, I'm going to write that larger as if it means something. All right? The total r that you would use in any of the formulas we just talked about, we would have to make sure that big R is equal to the height plus the radius of the planet. So be careful there with how some are worded. You just got to read it carefully. It'll just say the satellite is this far from the planet. If that's all they give you, go for it. But if they go, the object is this height above the planet, they usually use the word height for some reason. You need to make sure to include back in the radius of the planet as well to get the actual r for, if you're finding velocity, this r right here at the bottom. All right, so that's it. I mean, these problems are pretty straightforward. Just try to work through it. See it as a circular motion problem, and add in now, obviously, this idea of gravitational force. Thank you.